This is a video for OCR Pure Core Mathematics, Sequences and Series 2, Maclaurin Series, 2.2, the General Maclaurin Series. We've already seen how we can use a polynomial of this form to approximate some function fx. And we found the coefficients by evaluating the function and its derivatives at x equals 0. This approach can be generalized as follows. Here's my function, and then if you look, I've got a polynomial in ascending powers of x, and my coefficients are f0, f dash 0 over 1 factorial, second derivative at 0 over 2 factorial, third derivative at 0 over 3 factorial, and so on. And the term in x to the r, the rth term in this series, is the rth derivative evaluated at 0 divided by r factorial. You should look at your textbook for a more detailed treatment of this and a proper derivation. This series is called the Maclaurin Series of Fx. So here's my Maclaurin series written out up here, and we can use this to approximate a function provided we can work out the values of all of its derivatives at 0. So it must be continuously differentiable and it must have values that exist at x equals 0. If this series converges to a limit, then it converges to fx, and some Maclaurin series are only valid for a certain range of x values, and we'll look at those in our treatment of standard Maclaurin series in a later video. So let's have a look at this example. We're going to find the first three non-zero terms and the general term of the Maclaurin series for fx is equal to cos 2x. And the simplest way to tackle it is to have a look at a table. So here's my original function. Here's its first derivative. If I differentiate this, then when I differentiate sine, I just get cos, so I will get minus 4 cos 2x. And if I differentiate again, I'll get a sine flip. Cos is minus sine when you differentiate, and I'll get 8 sine 2x. And again, I'll get 16 cos 2x. Now let's have a look at these values when x equals 0. So f0 you can see here is 1. Sine of 0 is just 0, so that's going to be 0, and indeed so is that one, because that's just sine 2x. Cos 0 is 1, so this becomes minus 4. Cos 0 is 1, so this becomes 16. And so the first three non-zero terms of cos 2x, well, f0 is 1. F dash 0 is 0, so I can ignore that one. So the next term is going to be in x squared, and its coefficient is going to be minus 4 over 2, so it's going to be minus 2x squared. And then again, there's no term in x cubed, and so the next term is going to be in x to the 4, and that's going to be plus 16 over 4 factorial. Well, 16 over 4 factorial actually boils down to 2/3, so I could rewrite this as 1 minus 2x squared plus 2/3 of x to the 4. Now this series will in fact continue, of course, so we should have a continuation for that here. There's that written up more tidily for you. There's the confirmation of the derivatives, and there's the confirmation of their values at 0. And here, that's just the first three terms of cos 2x. Now we've also been asked to find the general term of the Maclaurin series, and so here we're going to extend the table on a little bit and see what happens. Well, we can see, I think, from this that every odd derivative we're going to get a sine 2x, which means we get 0, so we can ignore all the odd derivatives. And for the even derivatives, if you look at this, the even derivatives are going up by -4 every time. So cos 2x minus 4 cos 2x, 16 cos 2x. We would expect this to be -64 cos 2x. And so we would expect its value at 0 to be -64. And indeed what we've got here is times by -4 every time. So if I think about what I've got at the second derivative, I've got -4 to the power 1. At the fourth derivative, I've got -4 squared. At the sixth derivative, I've got -4 cubed. So the number of the derivative looks to be twice the power here. So this would suggest that this is -4 to the power r. And we would have expected this to be -4 to the power r cos 2x. If we think about the series for cos 2x, then for the general term I'd expect an even power of x, let's call that x to the 2r, and it will have a coefficient which is -4 to the power r divided by 2r factorial. And that will continue. Again, there's that written up more tidily for you. Using the table allows us to see the kind of pattern that's going on, and there's my general term there. Okay, so let's look at that example plotted up so that we can see it. The green curve is cos 2x, and the red curve is the polynomial of order 6 in this case, and I can alter the order of the polynomial and see what happens. The first thing to notice is that at n equals 7 there is no change because there isn't a term in x to the 7. So if n is equal to 7, I still only get up to x to the 6. And then as I push this on up, you will see that the polynomial gets better and better as an approximation, not so much that it's closer around 0, but that the range over which the polynomial gives a good approximation gets larger. And what I've got here is a quite reasonable approximation, as I said before, for cos 2x between -pi and pi. And if we were using some kind of calculator computer program to evaluate this, we'd have a pretty good way of evaluating cos 2x just by using a polynomial of degree 18. And calculating that is relatively straightforward. The next video in this sequence is 2.3, Maclaurin series of standard functions.